Hi guys, how are you? I think all are fine. So, today's in our class, we are going to know something about the waves. Already we have seen last two classes about the waves. Now, we are going to go forward. Okay, are you ready? Yes, I am ready. So, here, stationary waves. First one is stationary waves. Closed pipes, open pipes, stretched string, laws of transverse waves, Doppler effect, and beats. These are the concepts we have to know clearly in this lesson. These are the concepts we have to know clearly in this lesson. So I will explain each and everything one by one in clear way. If you have any doubts, you can ask me in the Zoom class. Okay, understand? Are you ready? Siddhama? Right, okay. Listen carefully. Observe what I mean. First one is a stationary waves. Stationary. What is meant by stationary wave? When two waves of the same phase and path difference are combined in opposite direction or interact in opposite direction, then the new wave formed is called a stationary wave. New wave formed is called a stationary wave. Suppose a wave is propagating in the forward direction like this. Here we get an obstacle. So it strikes the obstacle and started its return journey like this. Now this type of waves formed is called stationary waves. Stationary waves. Okay, so already you know that in transverse waves, what forms crescent troughs? Okay. In longitudinal waves, compressions and rarefractions. Okay. Now, in stationary waves, we get nodes and anodes. What we get? Nodes and two types of points. Those are called nodes and antinodes. Understand? Okay. Here you can observe. Suppose this is a wave from here to here. It is coming in this direction and obstacle came. Then it changes direction and moving backward. When these two interact, forms a stationary wave. This is the line what we think. Then this point on the line, this is the point. Here its displacement is 0 or minimum. Displacement or amplitude is minimum. Amplitude is minimum. Minimum amplitude, minimum. These points are called nodes. So amplitude of a node is minimum. If it is 0, then what happens we will see. Minimum amplitude. And these points where having highest amplitude is called antinodes. What are those? Antinodes. These are nodes and these are antinodes. Nodes and nodes. Nodes are minimum amplitude points. Nodes are minimum amplitude points. Antinodes are maximum amplitude points in the wave. Stationary wave. So nodes and antinodes are there. Then what about the phase difference? Phase difference. So phase difference of nodes is 0, pi, 2 pi and so on n pi, where n is starting from 0, 1, 2 and so on. N is 0 to. So it is denoted by generally kx, where is k is the constant, x is the path difference. Total kx is called the phase difference. Since kx is equal to 0, k is a constant, x must be 0. Then the path difference is 0. And if the phase difference is 0, path difference is 0. If the phase difference is pi, then the path difference is, you get lambda by 2. Lambda by 2. And kx kabatti, this value come. How we get, we will see later. Okay. Like, so phase difference is 0, pi, 2 pi and so on n pi. Then the path differences are 0, lambda by 2, 2 lambda by 2, 3 lambda by 2, 4 lambda by 2 and so on, n lambda by 2, where n is equal to 0, 1, 2, 3 and so on. This is about the node, characteristics of nodes. If you observe the characteristics of antinodes, okay, so antinode, generally denoted by A. Its amplitude is, it is having a maximum value, means amplitude here y is equal to a sine kx minus omega t. This is called displacement of this wave, displacement of the particle, displacement of the particle. A is called amplitude, kx is called the phase difference, So this value sine 0 is equal to 0, sine pi is equal to 0, sine 2 pi is equal to 0, sine 3 pi is equal to 0. So that's why phase difference is 0, pi, 2 pi, 3 pi. For that value kx 0 means then we have only sine 0 is equal to 0, amplitude is 0, total amplitude 0. Understand? Like that. If you take antinodes, the maximum value, sine total angle must be equal to 90. So that's why here pi by 2. Angle must be equal to 90. Pi by 2. Then sine pi by 2 is equal to 1. 1 into A is equal to 1. So amplitude is 1. And then the displacement. What is displacement? Amplitude is equal to 1. Got displacement is nothing but the distance of the particle from that point to another point. That is lambda by 4. Why it is lambda by 4? You can observe here. So the distance between two consecutive crests or troughs or two rare fractions and consecutive rare fractions and compressions is always equal to the wavelength lambda. In the stationary waves, at the same distance, if you observe, yes, from this point to this point is lambda. Now, stationary wave is formed like this. Now, this is lambda by 2 and lambda by 2, half. And again, this is half. This is lambda by 4. This is lambda 4. Lambda by 4 plus lambda by 4 is equal to lambda by 2. Lambda by 2 plus lambda by 2 is equal to lambda. It means the distance between the antinode and node is always lambda by 4. This is the part. Lambda by 4. This part is just lambda by 2. And this is lambda by 2. Total becomes lambda. And this part from this point to this point, the smallest part is lambda by 4. Lambda by 4 plus lambda by 4 becomes lambda by 2. Understand? Lambda by 2 plus lambda by 2 is equal to lambda. This is the explanation. Understand? So this is about the stationary wave. Next one is pipes. Next one is pipes. How many types of pipes are there? Generally, we observe there are two types of pipes. This is a pipe and this is. Both ends are open. This is an open pipe. One end is closed pipe. Both ends, if you close up both ends, then we didn't get a pipe. So we have only deal with open pipes and closed pipes. Okay. Then what happens? These types of pipes are formed. In closed pipe, always one end is antinode and another end is node. So, since this is a closed pipe, we get this type of diagrams. One end is node, another end is antinode. Since the distance between node and antnode is lambda by 4, this becomes lambda by 4. In closed pipe, the distance or length is equal to L is equal to lambda by 4. For the hormones means nodes. We will see later. First hormone, second hormone, third hormone. Like that we are getting the hormones. Whereas in the open pipe, both ends are antinodes. Both ends are antinodes. Understand? Yes. Like this we are getting, yeah. Sorry. This is antinode. This is antinode. This is node. Then what is the length? L is equal to, you can observe. అంటే A to AN plus NA అనుకున్నాం. Distance between antinode and node is lambda by 4 plus distance between node and antinode is lambda by 4. Then becomes lambda by 2. So in the case of open pipes, the length is lambda by 2, whereas in the case of closed pipes, the length is lambda by 4. Open pipes length is lambda by 2, closed pipes lambda by 4. This is very important. So length is, why it is lambda by 4 in closed pipe and why it is lambda by 2 in open pipe. This is very important. Next we have to find the equations for stretches open and closed. Next one is a stretched string. So stationary wave is over, closed pipes are over, open pipes are over, stretched strings. What is a stretched string? Already we have seen. So if you observe the guitar, violin, like string instruments which produce a sound, those strings are called stretched strings. And both ends of the string are tied to the fixed points. Fixed point. This is the one and A, suppose this is another and B. Then string is, yes, tied. This is called string. This is the stretched string. If you apply force on the middle of the stretched string, it vibrates. Yes, it vibrates. Then what you observe? Yes, this is node and this is node. This is antinode. This is the stretched string. Means, so one loop, the distance of one loop in a stretched string is lambda by 4 plus lambda by 4, that is equal to lambda by 2. Lambda by 2. So do you want any doubt? Okay, understand. If you have any doubt, ask me. I will explain. Observe this one. Next. What? Now we are going to see laws of transverse waves in stretched strings. Fourth one is, what are the laws governing the stretched strings? Already I told you the example that stretched strings we can observe in violin, guitar and all those things. So if we observe the guitar and violin, we can have chords like this. Suppose this is the guitar. Okay. Now here we can have strings, stretched strings like that. In that you are get notes like. So what are the properties of the transverse waves formed in the stretched strings we have to observe. Why we are getting one type of sound in one note and another sound in another note? It depends upon the main factors, the length, and this is fundamental frequency. The fundamental frequency depends upon some factors. That's why the distance, if you observe, the distance becomes less when it goes away from the string like this. You are getting more distance near here. Decreasing. Like. So the fundamental frequency depends upon the length, tension in the wire string, so that's why we are increasing its tension by screwing it, and the linear density of the wire. So linear density means that according to the thickness we get the density. So wire is in the form of a cylinder. Wire is nothing but the cylindrical shape with less radius. Cylinder 4/3 pi r cube. 4/3 pi r cube is the volume of the cylinder. So the volume. So density is equal to mass by volume. So m, mass of the wire by volume of the wire, gives the density of that wire. So linear density, mu, denoted by mu. So the fundamental frequency depends upon the length, tension and linear density. How it depends? You can see three laws. You can see the three laws. First law. What is first law? N is directly proportional to 1 by. What is N? Fundamental frequency. And fundamental frequency is 1 by L, inversely proportional to the length. Fundamental frequency is inversely proportional to length. Understand? It means that if the frequency increases, length decreases. If the length increases, frequency decreases. So depending upon the length of the wire, the frequency of the waves, transverse waves formed in that wire depends. Next one. Next law. Fundamental frequency is directly proportional to square root of T. What is meant by T? Tension in the wire. T is nothing but that tension. Understand? What is T? Tension. Yeah. T is nothing but tension in the wire. So if we increase the tension, then fundamental frequency increases. If we decrease the tension, fundamental frequency decreases. That's why by increasing tension, we can change the tone and also tune. Tone and tune we can say. This is nothing but sound. Next, third one. The fundamental frequency is inversely proportional to the square root of its linear density. Fundamental frequency is inversely proportional to square root of its linear density when length and tension are constant. Here three variables are there. One is length, another one is tension, another one is linear density. These three depends one upon each other. So if you want to describe one, we have to take another two as constants. Okay, so if you want to describe the length, then automatically tension and linear density are constant. If you want to explain tension, automatically length and linear density are constant. If you want to describe about the density, so what are those? Length and tension are yes constant. So these are the three laws of transverse waves. Laws of transverse waves in stretcher strings. Okay. Once again I am saying the first law. The fundamental frequency is inversely proportional to its length. You also say the fundamental frequency is inversely proportional to its length. Say again once. The fundamental frequency is inversely proportional to its length. In the same way, second law. The fundamental frequency is directly proportional to square root of its tension. The fundamental frequency is directly proportional to square root of its tension. Next, third one. The fundamental frequency is inversely proportional to square root of its linear density. These three are the laws. You can understand? Okay, next one. Next concept is Doppler's effect. What is the concept is Doppler's effect. What is Doppler's effect? I will explain clearly. Listen first. The apparent change in the frequency of sound due to relative motion between the source and the observer. The apparent change in frequency. What is that? The apparent change in frequency of sound. Why? Due to relative motion between source and observer. Source and observer is called Doppler's effect. Okay, now we see with an example. This is the source. Yes, what is this? Yes, aeroplane. Here is the observer. The frequency changes. The frequency changes as the relative relative motion. The relative motion between the source and the observer is called Doppler effect. Understand? What is that? The relative motion. Due to the relative motion, there is a change in the what? Frequency. Mainly on frequency. The change in frequency due to relative motion between source and observer is called Doppler's effect. Understand? Here we start. Main our frequency. What happens? There is a change in frequency. Why this change takes place? It is due to the relative motion. To whom and whom? To the observer and the source. So that's why we can say easily, without observing the aeroplane, we can say it is coming towards us or away from us due to change in the frequency. That is nothing but the Doppler's effect. Suppose if you are outside the railway station, when train is coming towards the station or it is going away from the station, we can say, without observing the train, by listening only the sound, due to change in the frequency, you can say very easily whether it is coming towards us or away from us. That effect is called Doppler effect. That effect is called Doppler effect. So, change in the frequency due to relative motion of source and observer. Then, next question. How many types of motions we get now here? What is a relative motion? Already you know. Relative means with respect to other. With respect to other. Here, source is there. Here, what is there? Observer is here. Source is there. Observer is. In this case, observer is at rest. Is sitting. Suppose you think he is sitting in the side. Observer is rest. Observer. Next is source. Observer rest. Source motion. Observer rest. Source motion. Rendu. Observer motion. Source rest. Third. Observer motion. Source motion. Case 1, case 2, case 3. There are 3 cases we can say. If both are at rest, there is no change in the frequency. So, gramophone is there, we are here. Continuously we are listening. There is no change in the frequency. Your TV and your place, you are watching film. There is no change. Both are at rest if you are in the chair, if you are sitting in the chair. So then there is no difference in the frequency. But when we get the change in the frequency, if one is constant and there is motion, or both are in the motion. So if one is constant and there is motion, that is called observer is rest, source in motion. Observer is motion, source in rest. Third one, both are in motion. So like that, depending upon this one, there are 3 cases to explain the Doppler effect. Instead, so train is at rest, you are in motion. There is a change in the frequency. You are at rest on the platform, change is moving away from the platform. Then you are also moving, train is also moving. Then there is a change in the frequency. So in this way, there is a change in the frequency, relative change in the frequency due to relative motion of the source and observer is called Doppler. So